March 7th, 1943, East Hartford, Connecticut. The Pratt and Whitney test cell shook with a violence that sent engineers scrambling for the emergency shutdown controls. Engine number R2808W, destined for a production F4U Corsair, had just completed its 97th hour of continuous operation when the timing chain failed catastrophically. Metal fragments tore through the accessory section like shrapnel, destroying the magnetos, fuel pump and oil pump in a cascading failure that turned 1,800 horsepower into 1,800 pounds of scrap metal in less than 3 seconds. For the third time that month, Pratt and Whitney's production schedule had been devastated by a problem that nobody could seem to solve. The Navy needed Corsairs desperately. Marine squadrons in the Pacific were flying aircraft with engines that had already exceeded their safe operational limits. Pilots were reporting power losses during combat that left them vulnerable to Japanese fighters who could exploit any mechanical weakness. But the R2800 double wasp engine, the magnificent piece of engineering that made the Corsair the most powerful carrier fighter in the world, had a fatal flaw hidden deep in its accessory drive system. The timing chain that synchronized the engine's camshafts and drove its critical accessories was failing with terrifying regularity. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Conventional wisdom said the problem was unsolvable within the engine's existing architecture. The chain had to operate at temperatures approaching 400 degrees Fahrenheit while transmitting forces that would snap conventional motorcycle chains like thread. It had to maintain precise timing despite shock loads from combat maneuvering and carrier landings that subjected the entire power plant to forces no peacetime engine had ever experienced. Most damaging of all, it had to survive in an environment where proper maintenance was a luxury that combat squadrons could rarely afford. But one machinist at Pratt and Whitney's experimental shop refused to accept that America's most important fighter engine had to choose between power and reliability. His solution would emerge not from advanced engineering theory or revolutionary new materials, but from an understanding of metallurgy and mechanical design so profound that it seemed almost instinctive. The timing chain that Frank Novotny would create in the spring of 1943 would transform the R2800 from a temperamental powerhouse into a mechanical marvel that could operate for 400 hours without failure, enabling the Corsair to dominate Pacific skies through tactics that would have been suicidal with less reliable engines. The wreckage from Test Cell 7 lay scattered across the concrete floor like pieces of a deadly puzzle that nobody wanted to solve. Leonard Hobbs, Pratt and Whitney's chief engineer for the R2800 program, stood among the debris with the exhausted expression of a man who had seen this failure too many times before. The timing chain had disintegrated at approximately 97 hours of operation, well below the minimum 200-hour requirement that the Navy contract specified. But the real problem wasn't just the hours, it was the pattern. Every chain failure followed the same sequence. First, individual link pins would begin to wear at accelerated rates due to inadequate lubrication in the high-temperature environment. Then, the worn pins would allow the chain to stretch, throwing off the precise valve timing that the engine required for optimal performance. Finally, when the stretch exceeded critical limits, the chain would skip teeth on the drive sprockets, causing the camshafts to lose synchronization and the engine to destroy itself through valve-piston contact. The R2800 double wasp represented the cutting edge of aircraft engine design in 1943. Its 18 cylinders, arranged in 2 banks of 9, produced a maximum output of 2,000 horsepower at 2,700 RPM, nearly double what most fighter engines could achieve. The twin-row radial configuration allowed enormous displacement in a relatively compact package, while the 2-stage supercharger maintained power output up to altitudes where most engines gasped for air. But all that power meant nothing if the timing chain failed during combat. Commander William Leonard, from the Navy's Bureau of Aeronautics, had made the situation brutally clear during his last visit to East Hartford. The F4U Corsair was the most capable carrier fighter in development, but carrier operations demanded reliability that exceeded anything required of land-based aircraft. A fighter that lost power during a wave-off could end up in the ocean. An engine that failed during a maximum power climb from a deck launch could kill not just the pilot but the deck crews below. The Navy would not accept an aircraft whose engines failed predictably at less than 100 hours of operation. Pratt and Whitney's engineering staff had spent months trying to solve the timing chain problem through conventional approaches. They had experimented with different chain designs, testing roller chains, silent chains, and even gear drives that eliminated chains entirely. They had tried various lubricants, from straight mineral oils to exotic synthetic compounds that were supposed to maintain their properties at elevated temperatures. They had modified the engine's accessory case to improve oil circulation and reduce operating temperatures in the chain chamber. Nothing had worked. The fundamental problem was that the timing chain operated in an environment that violated every basic principle of proper chain lubrication. Conventional wisdom held that chains needed constant oil bath lubrication to survive under heavy loads, but the R2800's accessory section couldn't accommodate a separate oil bath without adding weight and complexity that would compromise the engine's power-to-weight ratio. Instead, the timing chain received splash lubrication from the general oil supply, which meant that oil reached the chain only intermittently and at temperatures that degraded its lubricating properties. Frank Novotny had been watching these failures with the quiet frustration of a craftsman who understood that engineering theory sometimes missed practical realities that were obvious to anyone who actually built things with their hands. At 52 years old, he had spent 3 decades as a tool and die maker, creating the precision components that allowed Pratt and Whitney's engines to achieve tolerances measured in 10,000ths of an inch. He had never earned an engineering degree, had never taken a formal course in metallurgy or thermodynamics, but he possessed something that couldn't be taught in any classroom: an intuitive understanding of how metal behaved under stress. Novotny knew that the timing chain problem wasn't really about lubrication. It was about material selection and heat treatment. The chains being used were manufactured from standard carbon steel that had been case-hardened to improve surface wear resistance. This was the same material used in millions of motorcycle and industrial chains, and it worked perfectly well in environments where temperatures remained moderate and lubrication was adequate. But the R2800's accessory section wasn't a moderate environment. It was a hellish combination of extreme heat, shock loading, and marginal lubrication that demanded materials that didn't exist in any supplier's catalogue. The breakthrough came during an evening in late March when Novotny was examining one of the failed timing chains under magnification in his workshop. The wear pattern on the link pins told a story that contradicted everything the engineering staff had assumed about the failure mechanism. The pins weren't wearing uniformly along their length, as conventional friction wear would predict. Instead, they showed concentrated wear at specific points where the rollers contacted them during the high-load phases of the engine cycle. This suggested that the primary failure mode wasn't simple friction, but rather a combination of friction and impact loading that created what metallurgists called fretting wear. Novotny understood fretting wear from his years of tool and die work. It occurred when 2 metal surfaces experienced small amplitude oscillating contact under pressure, creating tiny particles of metal oxide that acted as an abrasive compound. The only way to prevent it was to create a surface that was both extremely hard and extremely smooth, harder than conventional case hardening could achieve, and smoother than normal machining operations could produce. The solution, if one existed, would require materials and processes that pushed beyond standard manufacturing practice. By early April, Novotny had developed a proposal that seemed almost impossibly ambitious. He wanted to manufacture timing chains from a nickel-chromium alloy steel that was normally reserved for high-stress applications like aircraft landing gear. The material was expensive and difficult to machine, requiring special tools and techniques that would slow production and increase costs significantly. But its properties were exactly what the application demanded. The alloy could be heat-treated to achieve surface hardness approaching 62 on the Rockwell C scale, nearly 20% harder than conventional chain steel. More importantly, The nickel content gave it superior toughness at elevated temperatures, resisting the embrittlement that caused conventional chains to fail. The heat treatment process Novotny specified was equally unconventional. Instead of the standard case hardening that created a hard surface layer over a softer core, he proposed through hardening the entire link pin, then tempering it at precisely controlled temperatures to achieve a combination of hardness and toughness that conventional wisdom said was impossible. The process would require temperature control accurate to within 10 degrees Fahrenheit and cooling rates that demanded specialized quenching equipment. Most manufacturing engineers would have rejected the proposal as impractical for production, but Hobbs recognized that conventional approaches had already failed repeatedly. The first prototype chains were manufactured in Pratt and Whitney's experimental shop during the last week of April 1943. Novotny supervised every step of the process personally, checking dimensions with precision gauges and monitoring heat treatment temperatures with an obsessive attention to detail that impressed even the most experienced machinists. The link pins were machined from alloy steel bar stock, then heat-treated in a controlled atmosphere furnace that prevented surface oxidation during the hardening cycle. After hardening, each pin was tempered at 600 degrees Fahrenheit for exactly 2 hours, then slowly cooled to room temperature to relieve internal stresses. The finished chains looked almost identical to the conventional ones they were designed to replace, but the difference was obvious to anyone who understood metallurgy. When struck with a hardness tester, they produced readings that exceeded any production chain by substantial margins. When examined under magnification, their surfaces showed a finish quality that could only be achieved through precision grinding after heat treatment. Most importantly, when subjected to tensile testing, they demonstrated strength characteristics that exceeded design requirements by more than 30%. The first engine test began on May 2nd, 1943, in Test Cell 7, the same facility where so many previous chains had failed. Engine number R2810W was fitted with one of Novotny's prototype chains and instrumented with thermocouples and strain gauges that would monitor operating conditions. Throughout the test, the plan was to run the engine through a torture test that simulated combat conditions, rapid power changes, sustained maximum power operation, and frequent starts and stops that would subject the timing chain to shock loads far exceeding normal operation. For the first 50 hours, the engine ran flawlessly. Temperature readings from the accessory section remained within normal limits, and periodic inspections showed no signs of unusual wear on the timing chain components. At 100 hours, the point where conventional chains typically began showing signs of distress, Novotny's chain showed wear patterns that were barely measurable. The link pins maintained their original dimensions within tolerances of 0.5 of an inch, and the chain's overall length had increased by less than 1/64 of an inch, well within acceptable limits. By 150 hours, it was becoming clear that something fundamental had changed. The engine continued to operate with mechanical precision that seemed almost impossible given the harsh conditions. Valve timing remained stable, oil pressure stayed consistent, and most remarkably, the timing chain showed no signs of the accelerated wear that had always preceded failure in conventional chains. The nickel-chromium alloy was performing exactly as Novotny had predicted, maintaining its surface hardness despite temperatures that would have degraded conventional steel, and resisting fretting wear through a combination of material properties that couldn't be achieved any other way. The test continued through 200 hours, then 250, then 300. Engineers who had become accustomed to timing chain failures at predictable intervals found themselves watching an engine that simply refused to fail. At 350 hours, Hobbs made the decision to continue the test until something broke, or until they reached 400 hours, whichever came first. The engine reached 400 hours on June 18th, 1943, operating with the same smooth precision it had demonstrated on the first day of testing. When the engine was finally disassembled for inspection, the timing chain revealed itself to be in remarkably good condition. The link pins showed measurable wear, but the wear was uniform and predictable, occurring at rates that suggested the chain could easily survive 600 or even 800 hours of operation before requiring replacement. More importantly, there were no signs of the fretting damage that had always preceded failure in conventional chains. The surface finish on the pins remained smooth and uniform, preventing the formation of metal oxide particles that would have acted as abrasive compounds. The metallurgical analysis confirmed what Novotny had understood intuitively. The nickel-chromium alloy maintained its hardness and toughness at temperatures where conventional steel began to soften and lose its mechanical properties. The through-hardening process created a microstructure that resisted crack initiation and propagation, preventing the catastrophic failures that had plagued earlier chains. And the precision grinding after heat treatment produced surface finishes that minimized friction and prevented the microscopic metal-to-metal welding that caused fretting wear. Production implementation of Novotny's timing chain design began in July 1943. Though the transition was neither simple nor quick, the specialized alloy steel required lead times that stretched existing supply chains. The heat treatment process demanded furnace capacity that Pratt and Whitney didn't initially possess, forcing them to contract with specialty heat treating shops that could meet the stringent temperature control requirements. And the precision grinding operations after heat treatment required machine tools and skilled operators that were in short supply as the war effort absorbed manufacturing capacity across the entire industry. But the urgency of the situation drove solutions that wouldn't have been possible under peacetime conditions. The War Production Board prioritized nickel-chromium alloy allocation for timing chain production, diverting materials from lower priority applications. Pratt and Whitney invested in new heat-treating furnaces that could process timing chain components in batches large enough to meet production requirements, and the company established training programs that taught conventional machinists the specialized techniques required for post-heat treatment grinding operations. By September 1943, engines equipped with Novotny's timing chains were beginning to reach operational units in the Pacific. The first combat reports came from Marine Fighter Squadron 214, operating from Henderson Field on Guadalcanal. The squadron had been flying F4U Corsairs with conventional timing chains that required replacement every 80 to 100 hours, forcing maintenance crews to perform engine changes with exhausting frequency. Aircraft equipped with the new chains began accumulating flight hours at rates that seemed impossible: 150 hours, 200 hours, 250 hours. The engines continued running with mechanical reliability that transformed operational planning. Major Gregory Boyington, commanding VMF 214, documented the impact in his after-action reports with characteristic directness. His squadron had been limited to aggressive tactics by engine reliability concerns that made every high-power maneuver a calculated risk. Pilots had learned to baby their engines during climbs and avoid prolonged combat at maximum power settings because they knew that timing chain failures could occur without warning. The new chains eliminated those constraints. Corsairs could be flown at maximum power for extended periods without the constant anxiety about mechanical failure that had influenced every tactical decision. The psychological impact on pilots was as significant as the mechanical improvement. Confidence in their aircraft's reliability allowed more aggressive engagement of enemy fighters. Pilots who had previously broken off attacks to conserve their engines now pressed home their advantages, knowing that their power plants could sustain maximum output throughout extended combat. The Corsairs' speed and climb rate advantages over Japanese fighters became fully exploitable for the first time, transforming the aircraft from a capable but temperamental fighter into a weapon system that could dominate its operational environment. Maintenance crews experienced an equally dramatic transformation in their working conditions. Squadron maintenance officers had spent months managing complex schedules that balanced flight operations against engine overhaul requirements. Aircraft were constantly being rotated out of service for timing chain replacements that consumed man-hours the squadrons couldn't afford. Novotny's chains changed the equation completely. Engines that previously required major maintenance every 100 hours now operated for 3 or 4 times that duration, with only routine oil changes and minor adjustments. Technical Sergeant Michael Rodriguez of VMF 214's maintenance section captured the change in a letter home to his family in December 1943. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. He described how his crew had gone from replacing timing chains weekly to forgetting that timing chains even existed as a maintenance concern. The engines just ran. They ran through carrier landings that subjected them to shock loads that should have destroyed lesser machinery. They ran through tropical rainstorms that filled the accessory sections with moisture. They ran through dust storms that infiltrated every opening and contaminated the lubrication system. And they kept running with a reliability that seemed almost supernatural to men who had spent months dealing with constant mechanical failures. The improved reliability had strategic implications that extended far beyond individual squadron operations. Carrier air groups could maintain higher sortie rates because fewer aircraft were grounded for engine maintenance. Long-range escort missions became feasible because pilots could trust their engines to survive the extended high-power operation required for flights lasting 4 or 5 hours. And perhaps most importantly, the Navy's confidence in the Corsair as a carrier-suitable fighter increased dramatically once engine reliability reached levels that met the stringent requirements for shipboard operations. By early 1944, combat reports were documenting Corsair engine performance that would have been considered impossible just 1 year earlier. Engines were routinely accumulating 400 to 500 hours between major overhauls, with some units reporting individual power plants exceeding 600 hours before timing chain. Replacement became necessary. The economic impact was substantial. Each timing chain failure had previously required engine removal and extensive repairs that cost thousands of dollars in parts and hundreds of man-hours in labor. The improved chains reduced those costs to nearly zero, while simultaneously increasing the operational availability of the aircraft fleet. Intelligence reports from Japanese sources captured after the war revealed that enemy pilots had noticed the change in American fighter tactics. Japanese fighter units operating in the Solomon Islands documented encounters with Corsairs that seemed willing to engage in sustained, high-speed chases that would have been tactically unsound if engine reliability were questionable. The Americans were flying their aircraft harder and more aggressively than Japanese pilots could match, exploiting mechanical advantages that Japanese industry couldn't replicate. The success of Novotny's timing chain design influenced broader developments in aircraft engine technology throughout the remainder of the war. Other engine manufacturers began adopting similar materials and heat treatment processes for critical components in their own designs. The lessons learned about high-temperature alloy behavior informed the development of turbojet engines that would operate at temperatures far exceeding anything a piston engine experienced. And the manufacturing techniques developed for precision grinding of hardened steel components became standard practice across the aircraft industry. Frank Novotny received formal recognition for his contribution in February 1944 when Pratt and Whitney awarded him the company's highest honor for engineering achievement. The presentation ceremony was brief and understated, reflecting Novotny's personality and the wartime emphasis on practical results over public recognition. But the citation that accompanied the award captured the significance of his work with precision. His timing chain design had solved a critical reliability problem that threatened the operational effectiveness of America's most important carrier fighter. The solution had emerged not from advanced theoretical analysis, but from deep, practical understanding of materials and manufacturing processes that could only come from decades of hands-on experience. By mid-1944, virtually all R2800 engines leaving Pratt and Whitney's production lines were equipped with Novotny's timing chains as standard equipment. The conventional chains that had caused so many failures were relegated to spare parts inventories, used only when the improved chains were unavailable. Production rates had stabilized at levels that allowed the Navy to maintain adequate supplies of replacement engines while reducing the maintenance burden on operational squadrons. The timing chain problem that had seemed insurmountable in early 1943 had been solved through a combination of metallurgical expertise and manufacturing precision that exemplified American industrial capability. The final validation of the design came during the carrier operations of 1945, when Corsair-equipped Navy squadrons began participating in the sustained combat operations that characterized the final year of the Pacific War. Carrier air groups were flying multiple sorties daily, subjecting their engines to operating profiles that combined maximum power takeoffs, extended combat patrol at high altitude, and aggressive engagement of enemy aircraft. The engines absorbed this punishment with mechanical reliability that allowed the carrier task forces to maintain operational tempos that would have been impossible with less reliable power plants. Commander David McCampbell, the Navy's leading ace with 34 confirmed victories, flew Corsairs throughout his combat tour in 1944 and early 1945. His aircraft's engine accumulated over 450 hours before being replaced during routine maintenance, having never experienced a timing chain failure or any other major mechanical problem. McCampbell's combat reports documented numerous instances where he pushed his engine to maximum power for extended periods during engagements with Japanese fighters, tactics that would have been dangerously risky with earlier versions of the R-2800. The technical achievement represented by Novotny's timing chain extended beyond its immediate military applications. The metallurgical principles that made the chain successful, selecting alloys for their high-temperature properties, using through hardening rather than case hardening for components subjected to impact loading, and achieving precision surface finishes through post-heat treatment grinding, became foundational practices in high-performance engine design. These principles would influence the development of turbojet engines for the next generation of military aircraft and eventually find applications in commercial aviation and industrial machinery. The production statistics told their own story about the design's success. Between July 1943 and the end of the war, in August 1945, Pratt and Whitney manufactured over 30,000 R-2800 engines equipped with Novotny's timing chains. Timing chain failures in operational service dropped from approximately 1 failure per 800 engine hours in early 1943 to less than 1 failure per 15,000 engine hours by war's end. The improvement represented a nearly 20-fold increase in reliability, achieved through modifications that added less than $10 to the manufacturing cost of each engine. The economic impact extended beyond direct cost savings from reduced maintenance. The improved reliability allowed the Navy to reduce spare engine inventories because fewer engines required replacement due to catastrophic failures. Carrier air groups could operate with smaller maintenance staffs because engine work consumed less time and required fewer specialized skills, and pilot training programs could operate more efficiently because training aircraft accumulated flight hours faster when they weren't constantly grounded for engine maintenance. By the time Japan surrendered in August 1945, the timing chain problem that had threatened the Corsair program in early 1943 had been forgotten by everyone except the engineers and maintenance crews who remembered the dark days when engine reliability was a constant source of anxiety. The solution had become so thoroughly integrated into standard practice that newer pilots and maintenance personnel had no reference point for understanding how problematic the engines had been before Novotny's innovation. The post-war period brought recognition that had been impossible during wartime. Technical papers documenting the timing chain development appeared in engineering journals, providing detailed analysis of the metallurgical principles and manufacturing processes that made the design successful. Novotny himself presented papers at several technical conferences, speaking with the quiet authority of someone who understood that practical solutions often emerged from experience rather than theory. His presentations emphasized the importance of understanding material behavior at a fundamental level, knowing not just what specifications said materials should do, but what they actually did under real operating conditions. The timing chain design influenced the development of subsequent aircraft engines throughout the late 1940s and into the 1950s, when Pratt and Whitney developed the R4360 Wasp Major, a massive 28-cylinder radial engine that produced 3,500 horsepower. the accessory drive system incorporated timing chain designs that directly descended from Novotny's work. The materials, heat treatments, and manufacturing processes all reflected lessons learned during the wartime development of the R2800's timing chain. The larger engine's chains operated at even higher loads and temperatures, but they achieved reliability levels that would have been impossible without the foundational work that had solved the Corsairs' timing chain problems. The transition to turbojet engines in the late 1940s brought new challenges that required different solutions, but the fundamental principles that made Novotny's timing chain successful remained relevant. Jet engines required materials that could survive temperatures far exceeding anything a piston engine experienced, and they demanded manufacturing precision that pushed the limits of available technology. The metallurgical expertise and precision manufacturing techniques developed for timing chain production provided a foundation for developing turbine blade alloys and precision casting processes that made practical jet engines possible. Frank Novotny continued working at Pratt and Whitney until his retirement in 1953, contributing to numerous projects that benefited from his deep understanding of materials and manufacturing. He remained characteristically modest about his wartime achievements, insisting that he had simply applied common-sense machining principles to a problem that had been overcomplicated by engineers who thought too much and built too little. But his colleagues understood that his contribution had been far more significant than he acknowledged. The timing chain that bore his design had enabled one of America's most important fighter aircraft to achieve its full potential at exactly the moment when that potential was most desperately needed. The final assessment of the timing chain's impact came from an unlikely source. After the war, American technical intelligence teams examining Japanese aircraft engine development discovered that Japanese engineers had been aware of timing chain failures in captured American engines. They had attempted to develop their own high-reliability timing chains using similar materials and processes, but had been unable to achieve comparable results due to limitations in their metallurgical industry and heat-treating capabilities. The Japanese had understood what needed to be done, but lacked the industrial infrastructure to implement solutions that required precision manufacturing at scale. By 1950, the R2800 engines that had powered Corsairs throughout the Pacific War were being retired from military service, replaced by newer designs that reflected post-war technological advances. But the reliability standards that Novotny's timing chain had established became benchmarks that all subsequent engine designs were measured against. An aircraft engine that couldn't operate for 400 hours between major overhauls was considered unacceptable, a standard that would have seemed impossibly demanding in early 1943, but had become routine by war's end. The legacy of one machinist's understanding of materials and manufacturing extended far beyond the specific application that had driven its development. Novotny's timing chain represented a broader principle about how engineering problems were solved. Sometimes the answer didn't come from advanced theory or revolutionary new concepts, but from deep practical knowledge applied with intelligence and precision to problems that others had overcomplicated. The timing chain that made Corsair engines run 400 hours without failure was a testament to the power of craftsmanship and practical understanding in an age increasingly dominated by theoretical engineering and scientific analysis. The Corsairs that had flown combat missions with Novotny's timing chains were gradually retired to storage facilities or sold as surplus after the war ended. Most were eventually scrapped, their engines removed and stored in case they might be needed for some future emergency that never came. But the technical knowledge embedded in those engines survived, preserved in engineering documents and manufacturing specifications that would influence aircraft engine design for decades. The timing chain that had solved an urgent wartime problem became part of the permanent foundation of aircraft engine technology, a small component that enabled great achievements by doing one thing perfectly, surviving in conditions that would destroy lesser designs. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.